like all of you. All right. Hi, everyone on Zoom. Welcome. So many of you to show up. It was lonely in here. There was 3 people before the 2 boys showed up. They're not here yet. They will always show up. They'll be here in 5 minutes about. They sit in the back. They'll be here in about 4 minutes. They're always like 10 to 15 minutes late. It's like deliberate, I think.
I say like 5:30.
You think it's 5:30?
5:30. Between 5:30 and 5:40.
We need a betting pool on this. They would like that because we brought up gambling and they are complete degenerates.
No.
I was trying to load up the roulette table that had 2 zeros, and the first thing that came up was the one that had a single zero. And they said, look up American roulette. You'll find what you're looking for. I'm like, God damn, that's some degenerate shit right there. Like, and they actually talked to me after class. Wanted to ask about counting cards and all sorts of it. We had a long conversation. I know the process and I know the motivation for it. I'm not any good at it because you have to look like you're not counting cards while paying utter attention to everything. So this is 6.2 binomial probabilities.
I don't know if it's me, but it keeps like getting blurry. I don't know if it's my computer or. Okay, that's better.
Okay, make sure you tell me if I see some shit in chat. Is it all just saying it's black and blurry? Or is it saying hurry up, Jones, and teach? Nope, it was saying good evening. No, then I was gonna show it, but I fell asleep. Which is confusing because you showed up.
Probably like not enough driving time to get here.
Oh, I was gonna show up, but I fell asleep on Tuesday. That's what you're talking about. Okay. Stan, you're here, so you showed up. I don't understand what's going on. Oh, you meant today? Oh, okay. All right, binomial probabilities. On Tuesday, we looked at doing discrete random variables. All of the chapter 6 is when we're working with whole numbers. So the binomial probabilities is when we have, there's 4 criteria. We have to have, well, first off, there can only be 2 possible outcomes. Hence the by part. It's 2. And these possible outcomes have to be mutually exclusive. Which means no overlap. Each of these 2 possibilities come with a probability. The probabilities have to be fixed. Or unchanging between different trials. So like if I'm throwing a bunch of dice, each time I throw the dice, it's 1 trial. There has to be a fixed number of trials. Which means we can't have anything like no scenarios where it's once the event happens X number of times, And finally, the trials have to be independent. One can't affect the next. So the fixed probabilities, that's worth taking another gander at. Even A is worth taking another gander at. If I'm rolling dice, like 2 dice, I could go, how many times do I get a 7? Now, there's a lot of different outcomes for rolling 2 dice, right? I could get a 12, I could get a 10, I could get a 2. So there's a lot more than 2 outcomes. But if I narrow it down to either roll a 7 or not roll a 7, now there's only 2 outcomes. It just so happens not roll a 7 includes a lot of different rolls. But I either roll a 7 or I don't roll a 7 means I'm down to 2 outcomes, which fits that binomial part, the 2 part. Rolling dice, the probability doesn't change between rolls. I roll the dice, I pick them up, I roll them again, the probability stays the same. Works great. I can't roll them until I roll a 7, like you would maybe doing craps. But it's got to be like I roll 10 times and count the 7s. Not I roll until I get 3 7s.
Can you move it up, please? Thank you.
The idea of the probabilities being fixed and the trials being independent kind of go together most scenarios. If the probabilities are fixed, generally they're not affecting each other, like rolling dice. If I'm drawing cards, like I draw 10 cards from a deck of cards, and I'm counting how many hearts I get, I do have a fixed number of trials. I'm drawing 10 cards. But as I draw cards, each card I draw affects the outcome of the next card, as if I don't put them back. Like if I draw a spade, now there's 1 less spade to draw, which means my chances of getting a heart go up a little bit. If I draw a heart, I have less chances to draw a heart. So cards, drawing cards without replacement is bad. Replacement means once you draw the card, you put it back in the deck. Because the probability changes and it's not independent anymore. we'll take a look at some examples, decide. The hardest part about this is deciding whether or not a binomial probability applies. So we'll look at some examples. Make sure everyone has a chance to write this down. Are you good, Herlinda?
Yes, sir.
Oh shit, I'm going at a good pace then. Anyone online need it up longer?
I'm good.
So let's look at some examples. Which has you rolling 5 dice. And try to get 5 of a kind. All the dice are the same. And I want to count how many times I get a Yahtzee in 100 rolls. So this is a true story. Like the Yahtzee game, they come each sheet comes with like enough room to play 6 games. And I played it with my wife and her like cousin. And it's just like you play the entire sheet all at once, like a bingo card. So you just do whatever column you want. And then at the end, you add them all up. And so you can like be strategic. One time I got 8 fucking Yahtzees. Like normally I don't get one. One time I got 8 Yahtzees. It was crazy. That's just changing it up to slow a little bit. If you haven't played Yahtzee, that means you're young. Yahtzee's for old people that didn't have fucking computers and shit. And I want to see how many times I get Yahtzee. Is this a binomial experiment? So we got to check the 4 criteria. Are there 2 mutually exclusive outcomes? Get a Yahtzee, or I could get no Yahtzee. So yeah. Is the probability fixed? Yes, it is. I believe if you watch the videos from 5.1 to 5.3, I actually showed it in one of them. It's 1/6 to the 4th power is the probability of getting a Yahtzee. I think I did. So that's fixed, which means not getting a Yahtzee is 1 minus that. So that works. Is there a fixed number of trials? I indicated 100 rolls. So yes. And finally, are they independent trials? Yeah, dice rolls tend to be independent. So this is indeed a binomial experiment. FA wants to see how homework affects test scores. And I look at grades. Until I find 10 students current on their homework. Is this binomial? Okay, so are there two outcomes? Yeah, they are either current on their homework or they're not. Is the probability fixed? Assume so. I don't know how you would calculate the probability of a student being current on their homework, but I'll assume it's fixed. Is there a fixed number of trials? Why are you shrugging?
Would there be a fixed number of trials?
Give me a reason why it wouldn't be.
You can only have so many students. There's over.
It's not a fixed number of trials. You were right. It's not fixed. But it has to do with how many students I'm looking for. 10 students that are current.
If you don't have.
Well, it might be the first 10 students I grab. I might just go down the roster and the first 10 students are all current on their homework. Or it might be like the first 10, I don't have any in the first 10 that are current, and they're like sprinkled out over 30 students. And I have to go through 30 students' grades to do it. So I may not ever actually reach the 10 students. And if I do, it's random on whether or not it's in 10 students or more. So it doesn't meet the fixed number of trials. It's at least 10 students. It could be more. But it's likely more. Can't remember any class I've ever had that I could go down the fucking roster and the people that the top 10 alphabetically were good students and current on their homework. That's a lot of students in a row to be current on their homework. So this is not a binomial experiment. Anyone need it up longer? Holy shit, I'm going at a good pace. I hit the right stride, right here, Linda? That's a fuck, I hit the sweet spot. So what is this shitty formula? For binomials. If n is my number of trials, and p is the probability of success, and x is the value we are looking for, the probability of x equals n choose x times p to the x power times 1 minus p to the n minus x power. And if you're looking at that and going, hell no, I agree. This is a bitch. And easy to mess up. Thankfully, we have StatCrunch. You need the values n, x, and p for StatCrunch. But then we'll do stats, calculators, binomial. I didn't say you could leave. They didn't fucking show up and it's almost 5:40. Look at this. This is wrong. She said 5:30. I said 5:10 after 5:20. What?
I'm just looking at this.
Good. The n choose x might have been familiar. We were doing that in chapter 5.
Yeah, that's the thing.
So let's look at some examples. And then we'll do the example in Sacramento, and I'll show you why you don't want to do it by hand. I do not. I walk around with a notebook only. That's how I roll. Walks around without their charger. That's some, you are fucking way too smart for that shit. How are you not having your charger? Everywhere my laptop goes, I take my charger.
Yeah, I see.
The walls have sockets if you need to move next to the wall. Look at that, everybody but the rocket scientist child in here has a fucking charger. I'm fucking with Sebastian again. I don't know, one of these days he's gonna go home and like tell somebody that I'm picking on him. And then I'm gonna have to explain why I'm being verbally abusive to a teenager. And I'm gonna say I'm not.
I swear.
I'm gonna say, prove it. Oh shit, I got a recording. Oh, that's abusive, it's more heckling. I know you don't mind. If I thought you mind, I would not have done it at all.
That it does.
So I gotta entertain the smart ones. What? That's true. I gotta entertain the really smart ones, though. The ones that don't pay attention and still do well. I'm doing my physics homework. I'm writing my English paper. Those students. So here's our example. 35% of car owners have 3 or more cars. At home. We sampled 20 cars. To see if they have 3 or more. What is the probability that exactly 5 homes So we can go through the list of things to see if it's a binomial. The probability is fixed at 35%. We're doing 25 homes, so there's a fixed number of houses we're looking at. If we're picking the homes randomly and not all in the same neighborhood, there's no reason to think that they're dependent on each other. So that'll work. And what's the other one? Fixed number of trial. Oh, there's 2 outcomes. They either have 3 or more or they don't. So in this scenario, the number of trials, I said we sampled 20 cars. That is not what I meant. We sampled 20 homes. The number of homes we checked is our N, that's 20. The probability of success is 0.35. We're going to write that as a percentage of the decimal. And we're looking at X equals 5. So you could do this in a calculator if you wanted. This is 20, choose 5. N, choose X. And then we're going to do P to the X power. And 1 minus P to the N minus X power. Not that bad. It is doable in a calculator. It's not too bad. If you work this out, we'll do it in StatCrunch in a second. You get that. Before we look at the next one, I'm going to show you why we don't want to do this by hand, because this is a pain in the ass. What if it's less than 6 homes? Have 3 or more. Here, I'm looking at the probability that X is less than 6. Which means it could be 0, 1, 2, 3, 4, or 5. And for each of these, insert shitty formula for each. Before I do it on StatCrunch, I also want to show you a couple more examples in this area. So I'm going to write them down first so that you'll have them written down. You'll know what we're doing when we get there. So for C, we're going to look at least 1 home has 6 or more. Or has 3 or more, sorry. Which means we've got a couple options. If we were doing it by hand, we could do P of 1 plus P of 2 plus, and keep going, go all the way up to P of 20. Or we could use that complement rule we did in chapter 5. With the, when it's like at least one, the opposite, the only other thing it could be is 0. So we could do or 1 minus probability of 0. So that's actually doable by hand here. But stack crunch isn't going to require that. What we're looking at here is probability that X is greater than or equal to 1. Two more things we want to look at. Number of homes between 6 and 12. And number of homes between 6 and 12, including 6 and 12. They say inclusive there. So this is like doing probability of 7 plus probability of 8, going all the way up to the probability of 11, but not 6 and 12. Because 6 and 12 are not between 6 and 12. They're the boundaries. It's a word game bit right there. It's shitty, but that's just the way the game's played. Here, however, I said inclusive. So there we will do all of them. And we'll show how to do all of these in stack crunch. You guys ready? Are you ready? Unless are you ready? Yeah, you're
No,
ready.
I'm good.
Okay. Erlinda, good?
Yes.
All right, let's do it. All right, so we had, the first one we did was exactly 5. I'm going to go into stack crunch here. Don't need anything in the data table, kind of handy. Stats, calculators, binomial. They kind of show us like a mock-up of a histogram, except they're not touching. We have to change N, P, and X, and the sign. So N was 20 homes. There was 20 homes. Probability was 0.35. And I wanted exactly equal to X. And it spits out the probability right here. And that's what I wrote down on the other sheet. If you're paying attention, if you can see it well, either on Zoom or here, column number 5 is lit up in red. And all the other columns are black. It's showing us which column it's looking at. Okay, so that's handy. Because if it starts showing you some shit that you didn't think you were getting, then you put something in wrong. If we wanted to do probability that less than 6 homes have it, I can just say this is less than 6. Compute, and it gives me the value, and I will write that down on my sheet. Probability that X is less than 6 is 0.2454. I'll leave it at that. 4 decimal places is good. And I can see that only 0 through 5 are lit up. It's not including 6. We said at least 1. So I can change this to at least 1 by doing greater than or equal to 1. And this is a really high number. This has got almost all of them, as might be expected. I got the probability that X is greater than or equal to 1 at 0.9998. If you want to do the between things, see up here that it says between? Click on that. And now it's important to note, you cannot change the inequality signs. So if we want to do between 6 and 12, I cannot put 6 and 12 there. Because if I put 6 and 12 there, which is the last one we wanted to do. Notice it's got the column, this column for 6 lit up. It's got the column for 12 lit up. So this wasn't 7 through 11. This was actually the last one I wanted though, so I'm going to write it down while we're here. So this one is 6 is less than or equal to X, less than or equal to 12. And I'm getting 0.7486. If I wanted to do the between, I got to do the 7 and the 11. And I can verify that the columns that are red are only 7 through 11. And if I do that, I'm getting 0.5638 or decimal places. I'm writing what's in the box. I'll put it back up on the screen in a second if you want to see it. Each time though, for everything we've done, it's been in this box. It's in the box. Oh. And I was just writing in, I already had this stuff written down. I just didn't write, I was writing down the answers, that's all. We do have a little bit more in this section before we hit 6.3, the Poisson distribution. We like finding the mean and the standard distribution. So mu of X and sigma X for binomials. The easier one is mu of X, the mean is n times p. Sigma x is the square root of n times p times 1 minus p. And believe it or not, it's worth memorizing because we do n times p times 1 minus p for a bunch of shit, as we're about to see in a second. In the problem we just did, we had n was 20 and p was 0.35. So mu of x equaled 7. And standard deviation, n times p times 1 minus p, n times p we already did is 7. 7 times 1 minus 0.35. And then we take the square root, you're going to get 2.13307. Before I do the next part, I'm going to show you, switch back to stack crunch and show you what happens as we change p and as we change n, what happens on this problem. On the picture, on the graph. It's going to kind of motivate what we want. Anyone need it up longer? Okay. So right now it looks roughly bell-shaped. But if I change probability to something low, like 0.05, it doesn't look like a bell at all, does it? And as I get a little higher, it starts to get a little more bell-shaped. And it's sort of bell-shaped, but it's still skewed right here. If I go 0.5, it's perfectly bell-shaped. If I go really high, if I go up to like 0.95, it's skewed the other way. It's skewed to the left. That's with n equals 20, but if I make it like n equals 200 with 0.95, skewed some left, but not as noticeable. There's a bell now, I can see it. And if I said n is like 2000, that's a bell. So where this is going is what happens if n is low or p is low? So what we just showed, if n is low, it was at 20 when I was doing it. We had 3 outcomes. If p equaled 0.5, it was bell-shaped. If p was low, it was skewed right. And if p is high, it's skewed left. But as n got larger, it became more bell-shaped. So I'm gonna pause, let you write that down before we like discuss the next topic. Damn it, this is my chocolate day and I didn't do it. I didn't bring the chocolate, sons of bitches.
There's some in the
I was gonna
village.
say, yeah, there's.
I'm not, but that vending machine's fucking pricey. I'm not buying everybody fucking a bag of M&Ms. You'll see where this is going. When we do 6.3 in a second. Okay, so. And larger, but we want another, how do we make sure n is large enough? For a bell-shaped distribution. Whatever I'm doing, I can't change the probability. The probability is fixed, so I can't fuck with P. If P is too low or too high, the only other option I have if I want a bell is to change the number of trials I do. So we're going to go back to that n times P times 1 minus P that was in the square root. We want that to be greater than or equal to 10. And you'll know P. So let's try that P equal 0.95 that I was looking at. We just looked at it. What n do I want? This is n times 0.95 times 1 minus 0.95 is greater than or equal to 10. That's the criteria I want to meet. Without even figuring out what those are, I'm going to divide those over. If I divide, it puts them on the bottom over here. And then I pull out my handy dandy calculator. It is both handy and dandy. And divided by 0.95 divided by 0.05. I am getting n needs to be greater than or equal to 210.5263158. And I can't do some decimal version of n. So I need to round up regardless what that value is. I need to go up to 211. This will guarantee it's bell shape enough. Because later on, we're going to be doing a lot of stuff that has the empirical model, and we want to be able to use the empirical model, and the empirical model is a bell. It's a picture of the bell. It's got the plus or minus 1 deviation, the plus or minus 2 deviations. So the graph I've drawn like 4 fucking times. It sucks, but you'll memorize it one of these times. We want to be able to use that every time, and so we can force that with this. By picking n such that it works. Are you guys ready for 6.3? Six 6.3 has got a cool name. It looks like poison, but it's some French shit. It's pronounced Poisson. 6.3 is the Poisson distribution. It's got 2 S's, which makes it a little bit different than Poisson. Poison's only got 1 S. So, what are the requirements? Everything we've done so far has had requirements. Requirements here. The probability of 2 or more successes in a small enough interval is 0. Like the probability of prank calling someone twice in a row in under 0.5 seconds is 0. You just can't do it. The phone just doesn't ring fast enough. You can't do it. The probability of success is the same for any 2 intervals that don't overlap. And they need to be of equal length. I can't say 0.5 seconds on one set of prank calls and then do like 20 seconds on the next set. I can prank call someone twice in 20 seconds. It's doable. The number of successes in any one interval is independent of other intervals. Which basically means no overlap. When you're done writing, I will put up, I'll show you the website. I'm getting the data for the next scenario and we'll look at it. It's gonna wreck your world. I strongly recommend you don't ever look at it ever again for anything else that you eat.
It ruins the magic.
What's the point? None of it. It's the evil teacher inside of me. Check this out. The federal government has something called the food defect action levels. Food defect action levels are feed. And they actually have a website for it. The FDA.gov has a book. And you can start looking for what you're looking for. Scrolling down, looking for it. Where's the rest? It starts giving a list of products that you buy and what you might find in it. Like apple butter and mold count. Canned or frozen asparagus and infestations with beetle eggs. We're going to go down to chocolate. This is why this is normally M&M day. And I let every student eat M&Ms to their heart's content. And then I show them this because I am a dick.
So then you should have bought them.
That's what I'm saying. I was mad that I forgot. I normally do. I don't know. It's too expensive. I can get a box of M&Ms at Smart and Final for a decent price. That's what I normally do. Insect filth. We look at rodent filth or shells isn't the same. Rodent filth is pretty good. Insect filth though, average is 60 or more insect fragments per 100 grams when 6 100-gram subsamples are examined, or any one subsample contains 90 or more insect fragments. That's what I'm going to use in this next thing. So I'm showing you that, I'm just showing you where I got it. That I didn't just make this shit up. So let me get a new page for it so we have room. So the food defect action level for chocolate. Chocolate, which is FDAL. If you want to look this up later and ruin your life. Is 60 insect fragments per 100 grams. Now, this includes like eggs, wings, legs, larvae, just bug parts. So if I were to rewrite that, this is 60 parts per 100 grams. Which is like 0.6 fragments per gram. A Hershey bar. Bar, we don't need to do king size or mini. The standard Hershey bar is 1.55 ounces, which equals about 43 grams. We want to look at the probability of finding exactly 3. Exactly 3 fragments. We want to look at the probability of finding less than 3. And we'll look at the probability of finding at least 3. So Sebastian might actually like this formula. The Poisson distribution formula has the probability of x equals lambda t to the x power divided by x factorial times e to the negative lambda t. It's some complicated math shit. None of you want to do this by hand. I don't want to do this by hand, and I know what everything says. But what matters here is lambda is the average rate of occurrence. T is the length of the interval. And this is often time, but not always, like in this problem, it's not time. And X is the number of successes. We don't give a shit about any of that. We're gonna do stack crunch. So in stack crunch, in stats, calculators, Poisson. And it requires X and mu of X. So I kind of need to tell you what those formulas are before we go on. Mu of X is just lambda times T. It's spelled lambda. It's a Greek letter. And the one we don't need, but we should know how to do it anyways. The standard deviation is actually pretty easy. It's the square root of lambda t, which just means it's the square root of the mean. So let's look at what we have for Hershey right here. Until everybody's done writing it down, because I'm getting a little zippy over here. So for the Hershey problem, T was my intervals, and it looks like we're doing things in grams here, because it was 0.6 fragments per gram. So we want T to be in terms of that. So for the Hershey thing, T was 43 grams. And we actually had we calculated that there was 0.6 fragments per gram. That's the average. So that's actually lambda. Lambda is 0.6. which means if I want mu of x that I need for the problem, I need lambda times t, which is 0.6 frags per 1 gram times 43 grams. And if you multiply that out, you get 25.8. And as a reminder, we were going to look at probability of exactly 3 fragments. Fewer than 3 fragments, or at least 3 fragments. And you're gonna be surprised at how big of that number that is. So let's throw in a couple more. Let's say at least 10 fragments, at least 20 fragments. And fuck it, why not? At least 30 fragments. 30 bug parts in a single chocolate bar. What's the probability you buy a chocolate bar, it's gonna have at least 30 bug pieces? I don't know how they measure some of this shit. Like some bug parts get pretty small. How small is like a fragment? I don't know.
But I was like, I know there's too much. Right.
Right. So what I'm going to do when we put it in StatCrunch and I start writing shit down, I'm just writing shit down next to this. So you know what I'm writing down, where I'm writing it down. Sweet corn canned. Insect larva that is two or more of 3 millimeters or longer. So they gave a length. Corn husk for tamales. I don't want to read that to you. There's too many people that like tamales. That's some dirty shit right there. Let me click on back over to StatCrunch before I switch screens so that you don't accidentally see it. I'll protect you from me. All right, that was our binomial calculator. We don't want that shit. We want stats, calculators, Poisson. The mean we calculated, that was the 25.8. And we want it exactly equal to 3. That's a really small number. How many zeros is that? Shit, that's a lot of zeros. 2, 3, 4, 5, 6, 7 after the decimal point. So 7 zeros after the decimal point, and then a 2. That's really low. What if we look at fewer than 3? That's even lower. E to the negative 9. I'll have to show you that in a second. I'll write it down right now. 441 e negative 9. So this is what it gave me for less than 3. And I'll show you how to translate that in a second. If we looked at least 3, probability is 1. It's just flat out fucking guaranteed. Every candy bar has at least 3 insect parts. Guaranteed. 1. So let's check like, well, what about like 10? At least 10 is 0.999, and if I round 9. 99.99% chance of 10 insect fragments. Or more. About 20. .8965, still almost 90% chance that a candy bar, any given candy bar that you eat, Hershey's, well, any chocolate bar, doesn't have to be Hershey's, it's chocolate in general. Any chocolate bar has a 90% chance to have 20 insect fragments. 0.8965. What about 30? It's gotta go down eventually, right? Well, that's lower. That's only 0.2284 if I round. Which is a 22.8% chance. There's a lot of insect bugs in the chocolate we eat. Normally, this follows handing out chocolate to everybody and letting them enjoy it, because that's who I am. No, I just done forgot. You got spared by my own old age, basically. You guys ready for another? You guys ready for me to do a homework problem? Do a homework problem, what? Say what? Let's do a homework problem. And the reason why I'm gonna do a homework problem is if I don't, I'm gonna get a shitload of emails going, how do I do this homework problem? So we're looking at chapter 6. Number 19. For the past 15 years, or 115 years, a certain state suffered 27 direct hits from a major category or major hurricane category 3 to 5. Assume that this was typical, and the number of hits per year follows a Poisson distribution. That's a good thing about Poisson distributions. They often tell you it's a Poisson distribution. Compute parts A through D. What is the probability that the state will not be hit by any major hurricanes in a single year? So, this is problem 19. Chapter 6, problem 19. This is a hurricane problem. And my information says 115 years, 27 direct hits by major hurricanes. And question A is the probability that the state will not be hit in a single year. Now, we saw from StatCrunch, we need to know what X is, and we need to know what mu of X is. X represents that a state is not hit in a single year. What number does X equal? where X is the number of storms or major hurricanes it takes in a year. No. We do not want it to be hit in a single year. If it's not hit, how many times has it been hit? 0. Most students don't know what the hell they're like, what? 0? That's an option? What the hell's going on? Poisson's a lot going on in this problem, I get it. Mu of X, the average number of hurricane hits. It's got to be over some interval. And the interval they're giving me is a year. So the average number of hurricane hits in 1 year. So the way the question is prompted tells me what the T is. Well, now I just got to figure out how can I get mu of X with the information I was given. The only other pieces of information I were given was the shit at top. Hurricane hits, it says there was 27 hits. And that occurred in 115 years. Now, I'm going to write down as many decimal places as my phone will show me. Because I know if I round, it's going to fucking tell me I'm wrong. Because it likes to do that. 27 divided by 115. 2, 3, 4, 7, 8, 2, 6, 0, 8, 7. That's my mu of X. And for this first part, I'm looking for the probability that X equals 0. Which represents no hits. Nice, Kaylin. In chat for the Hershey's problem, she just typed extra protein. Your Hershey's is a protein bar. It's fucking great. I love it. Yeah, you know, I need a protein snack. Let's go get a Hershey's. It fucking works. All right. Those are the values I'm going to use. Let's go over to StatCrunch. And I already got StatCrunch open, so I'm just going to hop back over to it. I'm going to go stats, calculators, Poisson. And I calculated the mean as this value right here. I'm typing it in. Your values will differ. But I think seeing how it works is helpful. And I had X equals 0. 0.7907 4273. Giving it to me right here at the bottom of the Poisson calculator box. I will copy that and take that over to StatCrunch. Not StatCrunch, to the homework. I'll paste that in and see what I need to round to. It says 4 decimal places, so right. I'm rounding to the 7, the 4 says drop it. Now it says at least 1. I think I can have these up side by side. My fucking homework. There it is. So the probability says at least 1 major hurricane. That's X is greater than or equal to 1. And then again, it wants 4 decimals, so I need 5 and I can round. Rounding to the 2 and I have a 5 means rounding up to 3. Is this unusual? What makes something unusual? I've mentioned it a few times this semester. No.
It overlaps. No.
If it happens less than 5% of the time. That's what we're going to count as unusual. Unusual is less than 5% of the time. P is less than 0.05 or 5%. And I'll put that on the screen in a second so you can see what I wrote. Is this less than 0.05? Is 0.2093 less than 0.05? No. And that's how the rest of the problems are. It'll change how many years you're looking at. The hardest part on this one was figuring out what to do for mu of x and remembering what the hell unusual means, because you haven't really used it a lot yet. But we're going to start using it a lot. Which I have up here on the screen now. Less than 0.05 or which is 5%. That covers 6.3, and that's the end of chapter 6. Good stuff. Fuck out. Or work on your homework for 15 minutes.
Thanks, Teach.
You're welcome. Good one. You're fucking right.
Yeah.
I didn't say Doug. You're not intimidating. Doug requires intimidating. Oh, I gotta remember the fucking pillow. I don't know why you standing up made me think of that. I have no idea.
Because I walked in and I showed you this fish mode,
That's gotta be it.
probably.
Note to self in text message to my wife. This is the way I keep track of text messages. I send my wife a message and say, this is for me, don't read it. It's got fucked up, huh? Note to self. Upload a picture of the Game of Thrones pillow. That's better. Then I don't have to remember to bring it. Have a nice night, Kaylin and Maria. And anybody else that already left? Desiree, are you here? Let's find out.
Good night. Have a good weekend.
You too.
Thank you.